So to finish off the radians chapter, we've got section 5.5, and this is small angle approximations, and this is how this one works. If you look at a sine graph, so sine starts at 0 and does this, and then the negative part looks like this. So you can see that around 0, when theta is small, so remember that the theta, the angle, is on the x-axis, well, when that's small, this graph here is sort of approximately equal to this straight line here, right? Hopefully you can sort of believe me on that. It looks, sort of straight line-ish. Now obviously when it starts curving it goes away from the straight line, but for small angles of theta, the straight line and the curve are kind of close to each other. So the question is, well, what gradient does this straight line need? And if you think about it, it will depend on what units we're using. So this point here, what are the coordinates of this point? Well, if we're measuring in degrees, this is 90, and this is a height of 1. If I'm measuring radians, this is pi by 2, so this is just over 1.5, and this is an angle of 1, okay? So it turns out if you're measuring in radians, this red line here has the equation y equals x, right? So in other words, sine theta, the curve, is close to theta, whatever the value of x is, when you are measuring in radians, okay? If you do the same thing with tan theta, and tan theta looks like this, and so what's the equation of this line here? Well, again, if you measure in radians, then that is the y equals x line. In other words, tan theta is approximately equal to theta when theta is small. Now, another way of seeing that is to think about this. If I have a circle with a radius of 1, okay, now if this is theta, then this arc length here is also a length of theta, isn't it? Because arc length equals r times theta, and in this case we've got a radius of 1, so this arc length is theta. And what are we saying? Sine theta is opposite over hypotenuse. Well, what is the opposite divided by the hypotenuse? If this angle gets smaller and smaller, well, if the angle gets smaller and smaller, can you see that this arc length and this opposite here get basically to be the same thing? So the sine theta is the opposite divided by the hypotenuse, or the opposite divided by 1, or if you like, this length here is just sine theta, isn't it? So sine theta is approximately equal to theta, because this height here is approximately equal to this arc length here. So there's another way of thinking about it. With tan theta, another way of thinking about it is that you have this side divided by this side, so it's opposite over adjacent, and that's going to be, well, as theta gets small, then opposite over adjacent gets smaller as well, doesn't it? This thing at the end gets very close to 0, so it's a little bit less sort of less of a nice way of putting it here, but you can see, as if we've got a small theta, then I've got a small number here divided by approximately 1, okay? Or if you like, you could see it as this adjacent angle to my theta here gets approximately equal to hypotenuse, doesn't it? And as theta gets smaller, those two things get closer. So you could think of it as tan theta is very close to sine theta, which is very close to theta when theta gets small. So that's sine theta and tan theta. Now, what about cos theta? Well, when cos theta is close to 0, what do we get? Well, here's the cos graph. And if you can see, if we're going to have an approximation when theta is small here, a straight line is not going to work, is it? It's a curve here. So what sort of curve? Well, this sort of curve kind of fits it. And what does that look like? Well, it looks a bit like a quadratic graph, doesn't it? And it turns out that a quadratic will do. And if we can find a quadratic that will take approximately this shape and that is basically the same as the curve when theta is small, and the quadratic that works, well, not surprisingly, it's got a negative coefficient of theta squared, right? Because it's an upside down quadratic. So 1 minus theta squared over 2 happens to be the right quadratic. Now if you're happy with that, that's great. cos theta is 1 minus theta squared over 2, approximately, when theta equals small, when theta is small. If you're measuring in radians, then this is the right quadratic. If we were measuring in degrees, we'd need some other numbers in there. Now, if you're not happy with that, here is a way of justifying it. We know that cos squared theta plus sine squared theta equals 1. So cos squared theta equals 1 minus sine squared theta. So in other words, cos theta is the square root of 1 minus sine squared theta. Now if theta is small, we know that sine squared is approximately equal to 1. So this is 1 minus theta squared to the power of a half. Okay, approximately. And 1 minus theta squared to the power of a half we can deal with as a binomial expansion. So that is approximately equal to 1 plus a half lots of the thing in the brackets with the 1 plus some other terms, which I'm going to ignore because theta is small, so I can just take the first two terms for a rough approximation, which is 1 minus theta squared over 2. Okay, so there's lots of ways of justifying it, and everything I've done so far in just over 6 minutes is just tell you these three facts. Now if you're happy to just accept these three facts, that when we measure in radians and theta is small, these things are true, then we can just apply them. So for example 20, we get things like sine 2 theta plus tan theta over 2 theta. What's that when theta is small? Well, that's approximately, well, sine 2 theta is going to be, well, if sine of something is approximately equal to the thing that I put into the sine, the sine of 2 theta is going to be approximately equal to 2 theta. Tan theta is approximately equal to theta divided by 2 theta. So that is 3 theta over 2 theta. In other words, 3 over 2, or 1.5. Okay, so that thing is approximately equal to 1.5 when theta is small. The only thing to watch out for is if you're using a cos approximation. I've seen an exam paper question recently that a group of mine found it in a mock, where we had some sort of trig expression that involved the cos squared, and the question was, show that this is equal to, I think it was, I don't know, 1 plus theta minus theta squared over 6. I don't know what it was, but it was something like that. Now if you worked the answer out by putting, all the coses in this nasty trig expression were changed into 1 minus theta squared over 2, all the sines were changed to thetas, all the tans were changed to thetas, and then we expanded it all and divided it all, and whatever algebra we had to do. And it came out as this, plus theta to the 4, I don't know, so there was a theta to the 4 term in there as well, okay? And a lot of people went, it was supposed to equal this, I must have done the algebra wrong because it hasn't equaled that. All you had to do was say, well, theta is small. So if I've got a theta to the power of 4 term, I'm just going to ignore it because that is close enough to 0. Close enough to 0 that I can just ignore it, okay? So just watch out for those ones. When we say theta is small, we can make these approximations, but we can also say that if I have theta to the power of 3 or theta to the power of 4 or theta to the power of 5, then a lot of the time we can just then ignore those terms because they'll be small enough that we can ignore them. There is no exact point at which you say, well, you can ignore these and not those, but as a rule of thumb on the on the A-level papers, if you have a power of theta which is bigger than 3, and we're assuming that theta is small, so 3 or bigger, we can just ignore those terms, all right? So we'll just go up to the theta squared term, and that's good enough for us. So that is Chapter 5 radians dealt with. Good luck with that.